New unpainted steel is relatively easy to clean, provided that the surface has not been exposed to corrosion in a chemical or marine environment. The biggest problem is likely to be removal of mill-scale deposits. Blast cleaning using either shot or grit can easily remove most mill-scale. An advantage of using grit for blasting is the simultaneous creation of an angular surface profile. New unpainted metals, such as aluminium or zinc, can be prepared by light blast cleaning to both clean and roughen the surface. Adequate adhesion of coatings to the prepared surface may be difficult to achieve any other way. Chemical or solvent cleaning may be possible, but special paint primers, such as acid etch primers, must then be used to achieve good performance. Mill-scale is formed by reaction between the hot steel and oxygen in the environment during the production process. As a result, the surface of newly produced hot-rolled steel is generally covered with blue-black deposits of mill-scale. The adhesion of mill-scale to steel is unpredictable and may vary from tightly adherent to lightly adherent. If the mill-scale is over-coated, failure of the coating can occur due to delamination of the mill-scale from the steel surface. Mill-scale is also relatively smooth, a factor which is significant for today's high-build, fast-drying coatings. Adhesion of coatings to smooth mill-scale may be poor, resulting in failure through loss of adhesion. Mill-scale is cathodic relative to bare steel. When steel is partially covered in mill-scale and exposed to corrosion, the cathodic mill-scale does not corrode, being protected by the anodic steel. Corrosion does take place at the anodic surface, and base steel is lost. This effect is the opposite of what is generally required. For best results, new steel should be cleaned by abrasive blasting to remove mill-scale and to provide an anchor pattern for optimum coating adhesion. Surfaces that have been exposed to the environment and have subsequently corroded may be more difficult to clean. The surface is often rough and may have deep pits and other irregularities. When chemical contaminants have become bonded to the surface through a chemical corrosion reaction, removal may require special treatment. The processes used for cleaning corroded steel are generally the same as those used for cleaning new steel, and include hand and power tools, blast cleaning, and perhaps water jetting. The choice of surface preparation method is often determined by the choice of coating system. Coatings should be matched to the degree of surface preparation desired or possible. If coatings are to be successful with very little surface preparation, they must be chosen for their surface-tolerant characteristics. Most coatings need better standards of surface preparation. Modern high-performance coatings are likely to require blast cleaning to a high degree of cleanliness, and in some cases may also require that the surface is free of chemical contamination. The degree of cleaning required is closely related to the type of coatings to be used, although in general a better standard of cleaning will provide better long-term protection from any coating system. Solvent cleaning is a method for removing all visible oil, grease, soil, drawing and cutting compounds, and other soluble contaminants from steel surfaces. It is intended that solvent cleaning be used prior to the application of paint and in conjunction with surface preparation methods specified for the removal of rust, mill-scale or paint. The standard SSPC SP1 is the only commonly used standard that formally governs solvent cleaning to remove oil, grease, dirt, soil, drawing compounds and other similar organic compounds. SSPC SP1 defines a variety of pre-cleaning methods, including those listed here. Water is a common, if not powerful, solvent and may be used to good effect in cleaning a surface. We'll discuss its use later when we discuss water blast cleaning and water jetting. In the use of any cleaning method, appropriate safety precautions must be taken. Also, it's important to thoroughly rinse surfaces, particularly when alkaline or acidic materials are used, to minimize the amount of soil remaining and to remove residues of cleaning materials that could adversely affect subsequent coating performance. Hand tool cleaning is a method to prepare steel surfaces by the use of non-powered hand tools. Hand tool cleaning removes all loose mill scale, rust, paint and other detrimental foreign matter. It's not generally intended that adherent mill scale, rust and paint be removed by this process. Mill scale, rust and paint are considered adherent if they cannot be removed by lifting with a dull putty knife. A standard which is commonly used to control the hand tool cleaning process is hand tool cleaning SSPC SP2. This is comparable to ISO 85011 ST2 or ST3. SSPC Viz 3, ISO 85011 or other visual standards of surface preparation agreed upon by the contracting parties may be used to specify the surface finish required or to verify the condition achieved. Both standards define the use of a dull putty knife to determine whether contaminants are firmly adherent or not. Note, some inspectors have been known to use a sharpened putty knife, which violates the standard. Tools used in hand cleaning include wire brushes, scrapers, chisels, knives and chipping hammers. When hand tool cleaning operations commence, certain procedures are followed. The surface is inspected to determine its condition and the presence of heavy layers of rust, and to detect any foreign substances such as oil, grease or dirt. Solvent emulsion cleaning may be specified or required to remove oil, grease or dirt. Heavy layers of rust should be removed by chipping. The surface is cleaned with any of the hand tools previously mentioned and then inspected prior to coating. The coating should be applied within the time period required by the specification. Manual cleaning is the slowest and perhaps the least satisfactory method of surface preparation. Normal tools used are wire brushes or scrapers or chipping hammers. The process is slow, labor-intensive and costly, with the end result still far from satisfactory. It is practically impossible to remove all rust and mill scale by this method. A complicating factor can be the reluctance of labor to engage in arduous manual tasks. Slow progress and deteriorating labor relations can lead to significant increases in the cost of achieving a clean surface by these methods. Hand tools have the advantage of being portable and not requiring support power supplies. They're most suitable for use when small areas of work are to be prepared in the vicinity of other workers, or when access is difficult, such as when maintenance is performed on communication towers, 100 meters in the air. Manual cleaning should only be used when weather or some other factor precludes the use of another, more efficient process. Hand cleaning is one of the oldest methods of surface preparation. Generally, it's used only when power-operated equipment is unavailable, where the work is inaccessible to power tools, where the job is too small to warrant use of power tools. Power tool cleaning is a method of preparing steel surfaces by the use of power-assisted mechanical cleaning tools. These tools are essentially similar to the tools used for hand tool cleaning, but a power source such as electricity or compressed air is used. This process can remove all loose mill scale, loose rust, loose paint, and other detrimental foreign matter, but is not intended to remove adherent mill scale, rust and paint. As in SSPC SP2, mill scale, rust and paint are considered adherent if they cannot be removed by lifting with a dull putty knife. The standards most commonly used to govern the power tool cleaning process are SSPC SP3 or ISO 8501-1ST3. Power tool cleaning is frequently used in maintenance operations. In addition to removing loose mill scale, rust and paint, this method is used to remove weld flux, weld spatter and laminations, and to smooth rough welds, and round out gouges before abrasive blast cleaning. The machine design is of two general types: straight or in-line, or vertical or right angle. Shown here is a right angle wire brush. Overworking the surface with a wire brush may be detrimental because excessive burnishing develops a polished surface which provides a poor anchor for most coatings. Rotary power wire brushes can also easily spread oil and grease over the surface. Therefore, solvent cleaning is an essential step before power wire brushing. Problems with polishing the surface rather than providing a roughened surface are particularly likely with this technique, and mean that the use of rotary wire brushes is considered to be less desirable than other forms of power tool cleaning. A chipping or scaling hammer is the most widely used type of impact tool. A chisel is inserted into the power tool and the impact from an air-operated or electrically operated piston is transmitted to the chisel and in turn to the surface to be cleaned. Chisels may be of different shapes and materials. They should be kept sharp, otherwise they may drive rust and scale into the surface. Scrapers and special chisels can be suitably mounted into pneumatically or electrically powered impact tools. Scaling or chipping hammers are generally a slow, costly method of cleaning the surface, but in some cases, such as when considerable rust, scale or heavy paint formation must be removed, they prove to be economical. Great care must be exercised in using these tools because of the tendency to cut into the surface excessively, removing sound metal and leaving sharp burrs where the paint will fail prematurely. Grinders and sanders are often employed to prepare surfaces for painting. Machines used for this purpose may be the same as those used for power wire brushing, with suitable sanding discs or grinding wheels substituted for the wire brushes. The abrasive grit size used with this type of cleaning equipment must be selected properly. Too coarse an abrasive will create a deep anchor that may be unsuitable for good paint performance. An abrasive that is too fine may cause early clogging of the grinding wheel or sanding disc, thus making the process inefficient. Grinding is well suited for removing weld spatter, for smoothing weld seams, or for rounding off sharp edges or corners. Grinders are frequently used in repairing minor fabrication defects. The anchor profile produced can be extremely good, with complete removal of rust and mill scale. However, such methods of cleaning are very expensive for large areas. Also available are pneumatic and electrically operated sanders that have a flat pad or abrasive surface in contact with the metal to be cleaned. Some of these motor-driven sanders have an orbital motion. Flexible shafts are used on a small scale to operate rotary wire brushes and grinding wheels. On other grinding equipment, the discs or wheels are mounted directly to the main shaft of the motor of other portable or stationary units. In 1989, SSPC adopted a new standard, SP11, titled Power Tool Cleaning to Bare Metal. When the highest levels of surface preparation are required or specified, for example, SSPC SP11, production of a surface profile is a mandatory part of the surface preparation operation. Abrasive blast cleaning. Although this method produces surfaces that look like near white or commercial blast, they are not necessarily equivalent to those surfaces produced by abrasive blast cleaning. While quicker than using hand tools, the work is still labor-intensive and relatively expensive. Removal of rust and other contamination from the bottom of pits and irregularities in the surface is very difficult. In response to increased environmental regulations, many power tools have been produced with vacuum recovery systems designed to collect any dust, particularly old paint, generated by the cleaning operation. A major disadvantage to the use of power tools is the burnishing effect likely to be produced on the metal surface. This polishing effect, inherent with power tools, is the most unsatisfactory feature of this method. A polished surface affects the quality of paint adhesion, and the effect should be avoided if at all possible. Various degrees or standards of surface cleanliness achieved by abrasive blast have been defined. The abrasive blast cleaning standards for new steel most commonly used in abrasive blast cleaning applications are produced by NACE, SSPC or ISO. In October 1994, NACE and SSPC issued the following joint surface preparation standards for abrasive blast cleaning. NACE number 1, SSPC SP5, white metal blast cleaning. NACE number 2, SSPC SP10, near white metal blast cleaning. NACE number 3, SSPC SP6, commercial blast cleaning. NACE number 4, SSPC SP7, brush-off blast cleaning. These standards are roughly equivalent to the ISO standards that were developed from the original Swedish standards. ISO 85011 was published in 1988 and contains 4 standards. SA3, blasting to visually clean metal. SA 2.5, very thorough blast cleaning. SA2, thorough blast cleaning. SA1, light blast cleaning. Each system of standards represents a progressive scale of visual appearance only, the best grade being shown first in each case. The quality of blast cleaning is determined visually, and photographic standards are generally used for comparison purposes. There is no correlation between the degree of blast cleaning used and the surface profile produced, and no specific correlation with removal of chemical contamination or non-visible salts. For these issues, other standards and measuring techniques must be used. Particles of abrasive may be projected by direct feed of the particles from a pressurized container into a high-pressure airstream, pressure blasting, or by centrifugal projection from rapidly rotating impellers, centrifugal blasting or airless blasting. Abrasive recycled. The abrasive used in this case must be suitable for recycling. The size of blast unit usually varies with the job. Blast units can range in size from those holding 1.5 bags of abrasive for a small. Manual blasting should systematically cover the entire surface to be cleaned by moving the nozzle at fairly constant speeds in straight paths, each succeeding pass overlapping the preceding one and exposing clean metal without any discolored patches. The standard of blast cleaning should be no more and certainly no less than is required by the specification. The nozzle should be held close to right angles to the surface, but at a slight angle so that the abrasive does not bounce right back at the operator. Some surfaces, such as those with heavy mill-scale layers or with coatings such as thermal sprayed zinc or aluminium, are best blasted initially at a shallower angle, for example 45 degrees. The operator must be aware that this technique, while efficiently removing the existing coating layer, produces a reduced surface profile due to the angle of impact. Final blasting at right angles to the surface is required if the correct surface profile is to be achieved. Speed of nozzle traverse is dictated by rate of cleaning and should be as fast as will clean thoroughly without unnecessary dwell. Efficient use of the blast pot can save money in both man-hours and abrasives. The blast pot should be emptied daily if practical and kept dry to avoid contamination of the abrasive. Maintenance should be performed to eliminate leaks and eliminate pressure losses. The vessel should be inspected annually and hydro-tested to 1.5 times the design pressure to ensure effective functioning. Blast cleaning is a potentially hazardous operation. Safety with abrasives under pressure is very important. Remember that abrasives and air leave the nozzle at great speed, at a rate close to 450 miles per hour, 720 kilometers per hour, 660 feet per second, or about half the speed of a shotgun charge, and can impact on surfaces or other workers a considerable distance from the operation. The entire system, including hoses, operator and workpiece, must be grounded to prevent injury due to electrical shock. Grounding is particularly important when the operator is working at heights, when shock may lead to a fall, or when blasting in a hazardous environment. For the safety and comfort of the blast cleaning operator, it is essential that good quality working clothes are used. Typically, these would include safety boots with steel insert toe cap, coveralls, strong leather gloves, air-fed blasting helmet, incorporating a replaceable visor and leather cape. It is important that the operator has a good supply of clean, fresh air for breathing. Two common ways of achieving this are: a supply of air at low pressure is delivered from the blast pot via a filter. This method has the disadvantage of the air being the same quality, often poor quality, as that used for blasting. A separate supply of air, also at relatively low pressure, is fed from a remote air-driven pump well away from any contaminated or dust-laden atmosphere. Or the blast hose whipping around in the work area. The deadman valve could be considered to be cost-effective because it can eliminate the need for a pot tender or blaster's helper. Remote control valves may be operated by compressed air or electricity. Compressed air operated valves do not require any other power source than the compressor, but may be slow to react, particularly when the blast hoses and nozzle are a significant distance from the blast pot. Electrically operated valves operate instantaneously, but require a power source and are not intrinsically safe, so cannot be used in a hazardous environment. On completion of blast cleaning, the blasted surface should be cleaned to remove residual dust and abrasive. It may be blown down with a high-pressure jet of clean dry air, vacuum cleaned or brushed with a clean dry brush until there are no traces of residual dust or grit. The surface at this point in time should closely resemble the visual standard of surface finish that was specified. For example, NACE number 2, SA 2.5, etc. When dust or grit is not completely removed, it often remains hidden in crevices or corners. It can be disturbed by the high pressures of the paint spray stream and can be distributed into the paint film, causing a poorly adherent paint layer or an incomplete film. Surface profile may be measured with replica tape, a proprietary product produced by the Testex Corporation. Two types of tape are commonly used: coarse for 0.8 to 2 mm, 20 to 50 microns surface profile, and extra coarse for 1.5 to 4.5 mm, 37 to 112 microns surface profile. A piece of tape with a small square of compressible foam plastic attached to a non-compressible plastic mylar film is applied to the blast clean surface dull side down. A hard, rounded object, burnishing tool, such as a swizzle stick, is then used to crush the foam to the blast clean surface, causing the foam to form an exact reverse impression replica of the actual surface profile. The tape is removed from the surface and an anvil micrometer is used to measure the thickness of the foam and the plastic. The thickness of the mylar film, 2 mils, 50 microns, is subtracted from the micrometer reading, and the result is the depth of the surface profile. Surfaces must be free of oil and grease before blast cleaning. Blast cleaning will not remove oil and grease. All surfaces should be inspected after cleaning for compliance with the specification. Cleanliness after preparation is important. Residual traces of abrasive must be blown off, vacuumed or swept away before primer coating. Note, if lead is present in the paint waste or blast debris, the surface cannot be blown off. Contractor must follow all regulations regarding lead removal. Any scaffolding, staging or support steel above the surface must also be cleaned to avoid abrasive from dropping onto the freshly cleaned surface or onto the newly primed surface. Surfaces prepared for coating should not be allowed to deteriorate or to be contaminated in any way between grit blasting and spraying. Clean, grit-blasted surfaces should not be handled or touched unless hands are protected with clean gloves. They should also not be exposed for prolonged periods or exposed at all to atmospheric or storage conditions of high humidity, as under such conditions oxidation and rusting may proceed very rapidly. As far as practicable, any storage after blast cleaning should be in a warm, dry environment, and ideally, spraying should follow blasting as quickly as possible. Commonly applied rules indicate a maximum delay of 4 hours and require that if visible deterioration has occurred, the surface preparation shall be repeated. There are many standards related to surface preparation issued by many standards writing organizations. The ones that will be described in some detail in this module are produced by NACE International, formerly the National Association of Corrosion Engineers; SSPC, the Coating Society, formerly the Steel Structures Painting Council; ISO, International Organization for Standardization. The relevant standards will be discussed as they relate to the specific surface preparation method at hand. Ambient conditions may have an effect on the abrasive blasting process, as well as on the blast-cleaned surface before painting. Ambient conditions include air temperature and substrate temperature, relative humidity, dew point temperature, environmental exposure, for example, marine and industrial. It is unwise to abrasive blast if the steel surface is much colder than the surrounding air. Moisture may condense on the blasted surface, causing the surface to flash rust. The substrate temperature may be checked using a steel surface thermometer. When blast cleaning, high humidity, moisture, can result in rapid deterioration of the cleaned surface. Final dry abrasive blasting should not be performed in wet or damp conditions, that is, when raining or when the relative humidity is very high, generally greater than 90%. Relative humidity is defined as the amount of moisture, water vapor, in air compared with the maximum possible in the air, i.e. saturation level. If RH reaches 100%, then the air will not support any more water vapor, and a surplus would appear as condensation. For that reason, most coating specifications have a requirement that coating is not carried out if RH exceeds a certain limit, usually 85 or 90%. In addition, if air is saturated with water vapor, the evaporation of solvents is inhibited, causing problems with coating film formation. For this reason, coating specifications normally have a requirement that coatings should not be applied if the temperature of the steel or the surrounding air is less than 3 degrees centigrade, 5 degrees Fahrenheit, above dew point. Relative humidity and dew point are both calculated by making temperature measurements with a hygrometer. Dew point is defined as the temperature at which condensation occurs. If the ambient temperature falls below dew point, or if some or all of the structure has a temperature below dew point, then condensation will occur. Coatings applied over a wet surface will generally not achieve adequate adhesion to the substrate. If abrasive blasting is performed when environmental conditions are close to the dew point temperature, condensation is likely, and flash rusting may occur. The relative humidity and the dew point can be determined using a sling psychrometer and psychometric charts, which are discussed in the inspection module of this program.